In this video, we'll look at histograms, which are another way to picture quantitative data. And we'll learn some vocabulary we might use to describe the features of the data that we might see in the histogram. In particular, in this video, we'll focus on the shape of the data. The pattern of the values of data is called its distribution. A histogram is useful for visualizing the distribution. We can see whether the data tend to be close to a particular value or maybe multiple values, whether the data varies a lot or a little about the most common values, whether that variation tends to be more above or below the common values, and whether there are unusually large or small values in the data. Let's start with a histogram of life expectancy for the 197 countries and territories for which a 2011 value of life expectancy was available. The first step in constructing a histogram is to divide the data values into intervals or bins that are mutually exclusive so that they don't overlap, and exhaustive so that we don't miss any of the data. Bins are usually equal in size, but they don't have to be. The life expectancies range from about 48 to 83 years, so we've defined our bins to capture every decade from 40 to 90. The first bin includes countries with life expectancies at least 40 but less than or equal to 50. The second bin includes countries with life expectancies at least 50 but less than or equal to 60, and so on. The cut points are the values that define the bins, in this case 40, 50, 60, 70, 80, and 90. The vertical axis in our histogram is the frequency or count of the number of data values in each bin. We draw touching bars for each bin up to the frequency of that bin. Note that we can't read the actual data values from a histogram. From our first bin, we know that there are 9 countries or territories with life expectancies greater than 40 years and at most 50 years. But as an example, we can't tell from the histogram what the exact value of the minimum life expectancy is. The width and number of bins in a histogram can be any convenient value. However, it is possible to dramatically change the appearance of a histogram with the choice of bin size, particularly when the number of data values is small. As an example, if we change the bins to cover only a 2-year span, the life expectancy histogram appears to be more noisy, with more variation in the frequencies among bins. The tails of a histogram are the bars in the far left and right where the extremes of the data values are. Life expectancy has a longer left tail than right tail, corresponding to countries or territories with relatively low life expectancies. Here are a few examples of the range of shapes of distributions we can see in histograms. The histograms vary by the number of peaks and whether or not they have a peak, how symmetric they are, and how long the tails are relative to each other. From a histogram, we can get lots of information about the data. We can learn the peak of the distribution. If there is one peak, where it occurs is called the mode, corresponding to the most common bin of data values. We can learn the number of peaks or modes. A distribution can be unimodal, meaning it has one peak, or bimodal, having 2 peaks, or multimodal, having multiple peaks. A uniform distribution, in which all data values occur about an equal number of times, is an example of a distribution without a mode. From a histogram, we can also get an idea of the extent of spread in the data. We can also see the extent of symmetry in the distribution of the data. Histograms can be symmetric, which can be the case in unimodal distributions, distributions without a mode, or multimodal distributions. Left or negatively skewed, meaning it has a long left tail. Right or positively skewed, meaning it has a long right tail. We can also see deviations from the overall pattern, such as gaps in the data. Outliers are data values that are separated from the rest of the data because they are much larger or much smaller. Let's go back now and describe the life expectancy data from its histogram. There is one peak, so the distribution is unimodal. The mode is between 70 and 80 years. There is a much longer left tail than right tail, so the distribution is left skewed. And there are no outliers. We can see some of these features in the box plot of the life expectancies. I've rotated the box plot to be horizontal for ease of comparison with the histogram. Note that the median is in the right half of the box, and the left whisker is longer than the right whisker. This is typical of left-skewed distributions. We can also see these features in the 5-number summary. The difference between the third quartile and the median is smaller than the difference between the median and the first quartile. And there is less distance from the center, or median, to the upper extreme, or maximum, than from the center to the lower extreme. Also, in left-skewed distributions, the mean is less than the median, since the mean is pulled down by the values in the long left tail. Let's look at the histogram for another set of data, the differences between the estimated ages using the Lagrange method and the actual ages at death for our 400 skeletons. The distribution of these data is unimodal, with the peak between -10 and -20 years. Although there may be a few more values in the extremes of the left tail than in the right tail, the distribution is quite close to symmetric about the peak. And there are no outliers. Comparing the histogram and the modified box plot, we see that the box plot is also quite symmetric, with the median near the middle of the box and the whiskers of similar length. The data values outside the fences are not outliers here, since they are not separated from the rest of the data. This symmetry can also be seen in the 5-number summary. The distances from the median to the first and third quartiles are similar, as are the distances from the median to the minimum and maximum. The mean is a little less than the median because of the small lack of symmetry in the tails that we noted, but the mean and median are still quite close to each other. Note that the mean and the median both occur in the modal bin here. We can also look at the histogram for the 2012 salaries of the New York Red Bulls soccer team. The key feature of these data is the large gap between the salaries of the 2 players with the highest salaries, Marquez and Henry, and the 23 other players on the team. The salaries of Marquez and Henry are outliers. If we remove Marquez and Henry from the data, we can look at the distribution of salaries for the remaining 23 players. Players' salaries are bounded from below by a minimum that is imposed by the league. The resulting distribution of salaries is right skewed. The box plot shows this skew with the median slightly to the left of center of the box and a right whisker that is much longer than the left whisker. We can also see this lack of symmetry in the 5-number summary, with larger distances from the median to the third quartile and maximum than from the median to the first quartile and minimum. As well, we have a mean that is larger than the median. The 3 examples we just looked at all had unimodal distributions. That's because unimodal distributions are by far the most common. We'll now summarize what we've seen about the relative location of the mode, median, and mean in unimodal distributions. If the distribution is symmetric, the mean, median, and mode are all approximately the same. For a left-skewed unimodal distribution, the mode is typically larger than the median, which in turn is larger than the mean. And for a right-skewed distribution, the mode is typically less than the median, which in turn is less than the mean. Earlier, we looked at these 4 examples of some of the shapes of distributions that we can see in histograms. For the symmetric and right-skewed distributions, we can see the overall features of the shape in both the histogram and in the box plot. For the bimodal distribution, the box plot fails to capture the 2 peaks, so this is a situation where a histogram can be more useful than a box plot. Unimodal and symmetric distributions of data, with histograms that have roughly a bell shape, are very common for a reason that we'll see in coming lectures, and are very important in work that we'll be doing later in the course. For data with this shape, the standard deviation is an important measure of spread or variability. The empirical rule tells us how the frequency of data values is related to the standard deviation. In particular, approximately 68% of the data values are within the range from the mean -1 standard deviation to the mean +1 standard deviation. About 95% of data values are within the mean ±2 standard deviations, and 99.7%, almost all of the data values, are within 3 standard deviations of the mean. As an example of how well the empirical rule works, we can look at the difference in estimated age from skeletal remains and actual ages at death, which we saw has a unimodal and symmetric distribution. For these data, the mean is -14.2 and the standard deviation is 14.1. One standard deviation on either side of the mean is the range from -28 to 0, which covers 273 of the 400 data values, or 68.3%. Two standard deviations on either side of the mean is the range from -42 to 14, which covers 380 or 95% of the 400 data values. And 3 standard deviations on either side of the mean is the range from -57 to 28, which covers 397 of the 400 data values, or 99.3%. We can see that this is very close to the 68, 95, 99.7% that we expected from the empirical rule. Although it was derived from properties of symmetric and unimodal distributions, the empirical rule works surprisingly well in other situations. Let's see how it works for the life expectancy data, which is left skewed. I won't show all the calculations here, but the mean for these data is 69.9 and the standard deviation is 9.7. It can be shown that 128 of the 197 countries and territories in our data, that's 65%, are within 1 standard deviation of the mean. 186, or 94.4%, are within 2 standard deviations of the mean, and 197, all of the countries and territories, are within 3 standard deviations of the mean. We can see that even for this left-skewed distribution, we are very close to the 68, 95, 99.7% of the empirical rule. In this video, we've seen how to use histograms to picture the shape of a distribution of data values. In future videos, we'll see why this is such an important step in any data analysis.